So we've got these two small signal models, the hybrid pi and the T model. They're perfectly equivalent. We can use either one. It's just sometimes one works better than the other, but you can really make either work. But I recommend that you always consider things with the one that's easiest. And we've got these equations for GM for transconductance and for R naught. Three different ways that we can find GM: mu n C ox W over L V over drive, or square root of 2 mu n C ox W over L ID, or 2 ID over V over drive. They're equivalent. You use the equation that is the numbers that you have, that doesn't force you to calculate the saturation current, at least to find transconductance. So how do these numbers really change? I mean, what's going on there with this? So I'll try to leave that so you can see it. So if we had mu n C ox is equal to 126.5 microamps per volt squared, and we have a threshold voltage of 0.7 volts for an NMOS transistor, and we've got VA prime of 20 volts per micron, and L is 1.6 microns. We could find some values if we know V over drive and W over L. We could find the current, transconductance, 1 over GM, and R naught. 1 over GM is this resistance down here. If we use the T model, R naught of course is the source drain resistance, and at this point with the T model we usually just forget R naught, but later on we need to look at it and eventually. So we had a V over drive of 0.2 volts and W over L of 10. Then using the saturation equation is 1/2 mu n C ox W over L V over drive squared. If these models are only valid in saturation, so using that equation, we get 25.3 microamps, and we'd get a value of GM of 0.253. All right, let's move these over. Those are amps. We'll go with milliamps per volt. 1 over GM is ohms, and R naught is ohms. Okay, a little more room. So GM would be 0.253 milliamps per volt. And 1 over GM, the inverse of that is 3953. That's maybe a big value. I don't know. It depends on what you think. With this value of current and this VA and this L, we get 1.26 mega ohms. Quite a big value. Now, if we still had a V over drive of 0.2 volts, but we had a much bigger W over L, 100, then we get 250 10x microamps. Let's put microamps up there. And that would give us 2.53 milliamps per volt. And 1 over GM now, of course, will be 10x smaller, so 395. And but we lose quite a bit of our R naught there. We now have 126K. All these things may be scaling by 10x, but there's some of them that start to look like a very large change. If we made it even larger, 0.2, and 1,000, it's still reasonable up to that point. So now we'd have 2,500 microamps per volt, or 2.5 milliamps, or 2.5 milliamps, so 2,500 amps, microamps. That would give us 25.3 milliamps per volt, which is quite a big value. It would give us a very small resistance of 1 over GM of 39.5, but only 12.6 K. And that's so small that we might often have to include that R naught there. It's just to the point where it might be important. If we had a bigger V overdrive, and go back to that small value of W over L, 10, with that bigger overdrive and that square, we now have 316 microamps, quite a bit more current, right? And transconductance is much bigger too than it was up here. It's let's see, this milliamp, so it's 0.633, 1 over GM, 1579, so it's kind of on the big side still at this point, and 101K. That's not big at all considering what's going on there. For the same V overdrive, which is actually a pretty big value, if we have 100 for W over L, then we've got 3,100 microamps current and 6.33 milliamps per volt. Our 1 over GM is getting quite reasonably small now, 158, and 10.1 K, which is not a good thing. And if we go all the way up to 1,000, we've got 31,000 microamps, 63 milliamps per volt, 15.8 for that resistance, 1 over GM on the T model, and 1.01 K. And that's really a disaster for a lot of cases. R naught will be quite small, and so small as to make a lot of amplifiers work. There might be other cases where we want such a large W over L for a transistor, but with that kind of V overdrive, it just wouldn't really be a good combination. There's a lot of other ways that we could calculate these and look at those various interactions, but the interactions are important, and you don't want to